Okay, this is our second in the two-part series on fatty acid synthesis. Although really, if I was going to retitle this today, I would title it Fatty Acid Metabolism Regulation, because we're really going to be looking at the reciprocal regulation of both fatty acid synthesis and fatty acid degradation. So to kind of remember where we are in our metabolic map, it's this whole area. So we were going from acetyl-CoA through that malonyl up to the fatty acids, or kind of the reverse route here, back over here. So let's kind of review a little bit and look at the big picture. So we've talked about carbohydrate metabolism, right? So glycolysis, we got down here to pyruvate. We talked about fatty acid synthesis that was out here in the cytosol. We talked about beta oxidation, that fatty acid degradation. Talked about the formation of ketone bodies. And what I want you to really look at is, wow, acetyl-CoA is a really important central metabolite that plays into all of these. Okay, so we can get acetyl-CoA from carbs, we can get it from that beta oxidation, we can also form it from amino acids, which we haven't looked at. And then once we have it, there are various possible paths. The main one is we're going to go through that citric acid cycle, and then we're going to use those high energy electrons in that electron transport chain to set up the proton gradient for the ATP synthase. Okay, we also looked at its use in ketone bodies. And then in the last video, we saw that, hey, once our energy needs were met and we didn't need those ketone bodies, that this citrate that's made could be shuttled out. We regenerate that acetyl-CoA, and then we stored it as fatty acids. And remember, we store those fatty acids as those triacylglycerols. Okay, but we looked at mainly just to that fatty acid part. So when we talk about regulation, we have two things kind of going on, right? We have our fatty acid synthesis that occurs in the cytosol. We have our fatty acid degradation that occurs in the mitochondria. All right, and if we've got one of those happening, we probably don't want the other one happening. That would be a wasted effort, right? So we're going to talk about what enzyme regulates fatty acid synthesis and degradation. And it's that one that I mentioned last time was important, that acetyl-CoA carboxylase, ACC. All right, and this regulates both synthesis and beta oxidation. It turns out it's really important for both. So if you remember what that does, it added a carboxylate group, right? Just keep highlighting here. ACC adds a carboxylate group to acetyl-CoA. So if we come over here, you can see that carboxylate group. So the top picture was acetyl-CoA. The bottom picture is that malonyl-CoA. And that is the kind of activated version that we need in order to synthesize fatty acids. So there are two isozymes of this enzyme, okay? ACC1 is in the cytosol, so synthesis is occurring there. ACC2 is in the mitochondria, and in the mitochondrial matrix, and that's where that degradation occurs. But even though they're both in different places, they do the same thing. Okay, so they both synthesize that malonyl-CoA from the acetyl-CoA and bicarb. So it doesn't matter if that acetyl-CoA carboxylase is in, excuse me, in the cytosol or in the mitochondria. In both cases, its function really is to make this malonyl-CoA. All right, when that happens, acetyl-CoA, or the ACC converts acetyl-CoA to malonyl-CoA, which allows synthesis to move forward. So what I want you to do is I want you to stop and think for each of these situations, and right now we're just going to think about in the cytosol, we're going to think about synthesis of fatty acids. Would you want this to be active or inactive? All right, and I think you should pause the video and think about each of these and then pick it back up and compare what you get to what we talk about. All right, so pause the video and give it a try. All right, so if we look at these, number one, the bloodstream has a large concentration of fatty acetyl-CoA. So these fatty acids bound to our coenzyme A. If you already have lots of fatty acids in the bloodstream, probably we're not wanting to make more. And so we would expect this to slow synthesis. Okay, so we would expect this to be a negative effector of ACC. Okay, we would not, if you already have a bunch of fatty acids, we don't want to keep making more. All right, so if you have high levels of insulin, so if you have lots and lots and lots of insulin, think about what that means for your blood glucose levels, right? You have high blood glucose. And if you have high blood glucose, your energy needs are probably met. And so now you probably do want to synthesize, right? We want to activate our enzymes so that we can store some of that excess glucose or store some of this excess carbon that you've ingested as fatty acids. All right, the body has a large concentration of AMP. So we got to think about AMP, and we know that we make that when we need energy, right? Like we have, so here our body has energy needs. We have burned through a lot of our ATP. If that is the case, we do not want fatty acid synthesis, right? We want to save that acetyl-CoA for the citric acid cycle. Okay, so since ACC1, when it's active, helps us with synthesis of fatty acids, this would also be a negative effector of ACC1. Okay, and we'll look at what it does in a minute. All right, it has a high buildup of citrate. So citrate, if you remember, citric acid cycle, our oxaloacetate and acetyl-CoA combined to make citrate. And then if we didn't need energy, we didn't need the ketone bodies, that citrate gets ported out into the cytosol and can be made into these fatty acids. If we have a lot of citrate, this really means that our energy needs are met and our need for any sort of ketone body, our energy needs are met. So we want ACC to be active so we can store more of that, right? So we want this to be a positive effector. Speed up synthesis. All right, so what I really want you to realize is that what you're thinking about is, okay, is the situation the body is in one where you would want to store these things or one where you want to be breaking them down, right? Do we need energy? Do we have too much material? So that's what you're thinking of to make these predictions. Okay, let's take a look at how ACC is regulated. It can be both covalently regulated and allosterically regulated. So let's talk about covalent modification first, so phosphorylation. And in this particular case, for this enzyme, ACC, whether it's the ACC1 or ACC2, is more active when it does not have the phosphate. Okay, more active when it does not have the phosphate. And you can see that over here. Here's the one without the phosphate. That's our active carboxylase. Here's the one with the phosphate, inactive. Okay, it goes back and forth between with this AMP activated protein kinase. We often shorthand that with AMP kinase, AMPK. Okay, and so when we're going to activate that, we're going to phosphorylate. It causes it to become inactive. So when we activate the AMP kinase, it causes our carboxylase to stop, right? And so our carboxylase will now not synthesize the fatty acids. So will this get activated when AMP is low or when it's high? Okay, so we are going to want to, if we need energy, AMP would be high when we need energy. We are not going to want to use our acetyl-CoA to build fatty acids in that case, right? Because in that case, we're going to want to save that acetyl-CoA for energy. If we have lots of AMP, then we're going to want to save this for energy. All right, so sorry, pausing here. All right, because there's actually two things we should look at. There's two things that can activate this AMP, but I'm realizing I just put one of those in there. So one would be when we have high AMP concentration. All right, so activated when we have high AMP. That means our energy needs are not met. And then step back to the blood sugar. When are our energy needs likely to not be met? Well, that will be when you have low blood sugar, right? So if we have low blood sugar, we're going to expect to activate that AMPK, that kinase, all right, so that we can stop synthesis. Now, think about what hormone we've talked about that we see excreted during times of low blood sugar, and that would be that glucagon. Okay, so that glucagon will set off a various phosphorylation cascade, kinase cascade, that will eventually activate this AMP activated protein kinase, which then turns off the synthesis of fatty acids. All right, that was a lot. So these two circles are the circle and the square are our ACC carboxylase enzyme, active when not phosphorylated, inactive when phosphorylated. What will determine if it's phosphorylated will be these energy needs, right? So when we have low blood sugar, then we will emit glucagon, this hormone that will set off that cascade that will activate this kinase that adds that phosphate on here and deactivates the ACC enzyme. All right, that was a lot. Take a deep breath, and then let's look at allosteric effectors. Okay, so allosteric effectors, the first one we're going to look at is citrate. Because if we have a lot of citrate, we said, wow, that means it's not needed, right? If we have a lot of citrate, not needed in the citric acid cycle, so it must be available to be used. And you know what? We just like to start synthesizing some fatty acids, some fatty acids, right? Because we have plenty of materials for it. We don't have energy needs. We don't have material needs. So we're going to store that stuff as fatty acids. So to do that, it wants to activate the carboxylase, right? We want to activate it. Now, citrate can't add or take away a phosphate, but it does allosterically bind to some site on the enzyme. So notice that I have in both cases here the phosphorylated version. Now, citrate can also bond to the dephosphorylated version, okay? But it's really important here because it turns out that this, when it doesn't have citrate and when it's phosphorylated, is pretty much entirely inactive. But if we bond citrate to it, now it becomes partially active. All right, if you took active carboxylase and bound citrate, maybe it'd be more active. But man, here it's going from almost no activity to at least partially active. Okay, and the citrate kind of overcomes the inhibition produced by the phosphate. We'll look at the very end of this video about a little bit why. This is really important because citrate is going to be locally, in that particular cell, citrate will be locally either high or low concentration. For phosphorylation to happen, we've got to emit a hormone that has to go through that whole kinase cascade that eventually, all right, will come in and phosphorylate, or if it's the phosphatase, if we need to activate it, okay, we need to stimulate a different cascade that's going to start pulling those phosphates off. That can take a while. But since citrate is going to be increasing or decreasing in concentration locally, it can kind of get it kick-started. So before we can be fully active, at least citrate can kind of get it going while we're waiting for maybe all of them to be dephosphorylated. All right. And then we also talked about, I have a picture for it, that fatty acids, okay, are also allosteric effectors. We said that fatty acids, if you've got a buildup of fatty acids, we probably don't want to make more if we've got a bunch in the bloodstream already. Okay, so that's what we're talking about, fatty acids on those acyl carriers. And so they would be negative effectors. They are, again, allosteric. They're going to bond somewhere, and they're going to make it less active. All right, covalent modification of acetyl-CoA carboxylase, ACC, is regulated by a variety of hormones. So we already mentioned glucagon, okay, epinephrine, similar. So those inhibit the carboxylase by enhancing that kinase activity. That's what we looked at in the last one. On the other hand, insulin, which is a signal that we got high blood glucose, right? Well, if we got a lot of glucose, we could use some of this and start building up, go to our acetyl-CoA and then start building our fatty acids. So insulin stimulates the dephosphorylation and activation. So insulin would stimulate this process right here. All right, so let's just kind of review. So we have glucose going down to pyruvate. We made our acetyl-CoA, and now, hey, our citrate's been building up, so it gets ported out into the cytosol. So here was our mitochondria. Okay, that citrate gets broken apart into the acetyl-CoA plus the oxaloacetate, right? Acetate, I can't spell. Okay, but the part we care about here is that acetyl-CoA. And then here's what we've been talking about. This reaction right here, okay, that is taking acetyl-CoA to the activated malonyl-CoA. And then after we make the malonyl-CoA, now I can keep making the fatty acid, but this is our rate determining step right here, our control step. Right? We said a buildup of citrate would be a positive effector on our ACC enzyme. We said a buildup of the fatty acids would be a negative effector. And we said that if this AMPK is activated, that kinase, that's going to shut this down by phosphorylating it, right? And we said that that AMPK will be active when we have low blood sugar. Okay, low blood sugar, we have energy needs. All right. So let's talk a little bit about fatty acid synthesis and degradation. So we've already said, right, synthesis is in the cytosol, degradation is in the mitochondrial matrix. We would only want one of those to be active at a time, so we're going to have this reciprocal regulation. And we looked at things that are positive or negative effectors of ACC1. But y'all, they're essentially the same enzyme. So those same effectors will affect ACC2, but now it's going to be happening in the matrix. So real quick review. So here is a kind of blow up. So right here along that edge, okay, that's what's in this bigger circle here, is a little piece of that membrane. So we're on the matrix side here. So this piece would be inside here. Okay, we're in the inner membrane space, whoops, up here. All right, so that's out here somewhere, well, somewhere in that middle spot. If you remember from when we talked about fatty acid degradation, in order to be able to break down the fatty acids, we had to get them into the mitochondria. And when we did that, we had gotten them into the form of acetyl-CoA. All right, so shown right here. But that coenzyme A is big, and there is no transporter to transport it from the cytosol into the matrix, okay? And so we had to swap out that CoA for the smaller carnitine. So we got our fatty acid chain bound now to a carnitine. If you remember, here was our reaction. So we have our CoA, which is really big, right? But we're just abbreviating it. And it has our fatty acid chain piece right here, our acyl group. Carnitine is a smaller molecule than the CoA, and this hydroxide here is going to essentially grab that acyl group. So now we have our carnitine molecule with our acyl group attached. And that was good because there is a way to transport the acyl carnitine into the matrix. Once we get it there, we can swap that carnitine back for the CoA, so we've got our acetyl-CoA, so that we can start working on the degradation. Notice here, carnitine acetyltransferase. Those are our enzymes for this process to go. So to have degradation, we got to be able to get those acyl groups into the matrix, and we do that using this carnitine acetyltransferase enzyme. All right, why are we reviewing that? Well, it is because it's incredibly important as we talk about the regulation of the version of this enzyme in the matrix. So, same enzyme, y'all. So ACC2 is active when it's dephosphorylated, just like ACC1. And when ACC2 is active, it produces malonyl-CoA, just like ACC1. But it turns out we don't want malonyl-CoA in our matrix because it turns out it is a powerful inhibitor of these carnitine transferase enzymes. All right, so if we inhibit these transferase, we can no longer take our acyl group and put it on a carnitine so it can get into the matrix. So essentially, by having an active ACC2 in the matrix, we've allowed it to make this malonyl-CoA, but the malonyl-CoA is going to mess up this process, and so it's going to essentially inhibit fatty acid degradation. Okay, that beta oxidation, because that occurs in the matrix, but now we can't get the fatty acid into the matrix. All right, so if you think about this, when we activate ACC1, it can make malonyl-CoA, and now it can go on and synthesize fatty acids. When we activate ACC2, which will be at all the same times, we make malonyl-CoA, but that stops fatty acid degradation, right? When this is what we want. We want when one's going, we don't want the other one going. All right, so let's think about the effective energy needs on this reciprocal regulation. When energy needs are high, we'll make glucagon, right? We'll have glucagon, we'll have high levels of AMP. We do not want to be synthesizing fatty acids then. So that high AMP will activate that kinase, okay, or the glucagon will activate the kinase both inside and outside the mitochondria. So it acts on both ACC1 and ACC2. It phosphorylates them, which deactivates them. So now we have no active ACC enzyme. When it's deactivated, in the cytosol, it shuts down the synthesis, in both. It shuts down the synthesis of malonyl-CoA inside and outside. In the cytosol, that means that we shut down fatty acid synthesis. That is a step we've got to have for synthesis. So it inhibits synthesis. But in the matrix, it means that now we don't have that malonyl-CoA that was keeping us from getting the fatty acids into the matrix. So now we can start degrading them. So it stimulates degradation. All right, one last thing, because it's kind of interesting. So carboxylase, our ACC enzyme, okay, shortened to carboxylase right there, is active as a dimer, so two of them together, but even more active as a polymer. And so it turns out that citrate, okay, citrate activates the carboxylase. Remember we said even the inactive version with the phosphate could be partially activated by citrate because it facilitates this polymerization, okay, the formation of active polymers. So that citrate kind of mitigates whatever inhibition that phosphate had, lets these things polymerize, so they start getting some activity back. Palmitoyl-CoA, so an acetyl-CoA, not and, which is an acetyl-CoA, and is the one that is the end product of our synthesis, inhibits the carboxylase by doing the opposite. It causes the depolymerization. So if they need to be polymerized to be active, that palmitoyl-CoA keeps that from happening. All right, y'all. That was it for fatty acid metabolism regulation.